Okay, let's get started. Uh, Sorry about missing class last week. I got a little bit sick. I still have a bit of a lingering cough, so sorry if I end up coughing a bunch during lecture. Today we are going to wrap up our discussion on rasterization and then move on to our next topic, which will be ray tracing. But to follow up on the question that I got last in the previous class, um, when calculating the area of a triangle, there was a question about which two edges do we use to calculate the cross product for the area of a parallelogram. So the short answer for that would be that you can pick any of the two edges of a triangle. You don't have to explicitly form the parallelogram. You can just pick any of the two edges and use those two edges to do product. So the idea here was that we can take a triangle and we can mirror that triangle along any one of its edges to form a parallelogram. And I want to clarify a little bit about how this mirroring is done. So the mirroring to create a parallelogram is not exactly a mirroring along one edge. To form the parallelogram, we take the triangle and we rotate it by 180 degrees. And then we attach the triangle along one of those particular edges. And this will allow you to form a parallelogram given any edge of the triangle. So we are going to construct a parallelogram by joining two copies of the same triangle along any particular edge. And then we'll just pick the other two remaining edges as the edges that we use to calculate the cross product for the area of the parallelogram, which means that you can pick any edge you want. You can apply this formula to calculate the area of that parallelogram and then divide by half to get the area of the triangle. Okay. So with this method, we can calculate the barycentric coordinates for any point in our triangle by just applying the cross product to calculate the area of each one of the smaller triangles that we constructed using the point P, and then use the areas of those triangles to determine the barycentric coordinates, the interpolation weights, for mixing the colors that's defined at the three vertices of a triangle. Now, we have one last topic to cover for rasterization, which is how do we determine occlusion between multiple shapes? When we have a more complex scene, chances are there will be many triangles in the scene, and some of those triangles are going to be overlapping with each other. So in order to correctly render those triangles, we have to figure out how do we correctly order the triangles in terms of the distance to the camera. So a triangle that's closer to the camera should block any of the other triangles that are further away behind that triangle. And we have to handle these occlusions correctly in order to produce a realistic image of a scene. So for example, in this scene here, we have three triangles, a green triangle, blue triangle, and a gray triangle. And these triangles, they occlude different parts of other triangles in the scene. For example, the green triangle is the triangle that's closest to the camera. So it's going to block a bunch of pixels that overlap with the gray triangle. And similarly, the blue triangle is a little bit further from the camera than the green triangle. So the lower left corner of the blue triangle ends up being blocked by the green triangle. So when rasterizing triangles onto an image plane, we have to figure out which triangles are occluded by other triangles and only draw the triangles that are visible to the camera that are not occluded by other triangles in the scene. So a simple method that might come to mind for how to order the triangles that we are rasterizing would be by using a simple method called the painter's algorithm. And the idea with the painter's algorithm is that we are going to take all the triangles in our scene and we are going to sort them based on depth, based on the distance to the camera. So we are going to sort all the triangles starting from the furthest, starting from triangles that are furthest away to triangles that are nearest to the camera. And then when we are rasterizing the triangles, we are going to render the triangles one at a time, starting from triangles that are furthest away, and then moving towards the triangles that are closer and closer to the camera. So by rendering the triangles in this depth order, we are going to draw the triangles that are furthest away first, and then we are going to draw the closer triangles. And the triangles that are closer to the camera are occluding further triangles. Then the nearer triangles will overwrite the color values in the pixels that were drawn previously from the further away triangles. So in this simple scene here, we might draw the gray triangle first, which is the one that's furthest away from the camera. And then we'll draw the blue triangle, and then finally the green triangle. And this then allows us to correctly figure out which triangles are blocking some other triangles at each point in our image. Okay, so this is the simple painter's algorithm. Any questions about this?
Wouldn't this problem be like in a scenario where your region or your plane with all your objects, wouldn't that mean that if it's like, let's say something that's like open world where you have a whole bunch of elements in front of like this hole here, you're rendering everything behind it, but no users rendering it, and it's like performance wise, it's slow.
Oh, right, yeah. So one of the drawbacks of this algorithm is that your objects that are further away will always be rasterized into your image plane, even though they might be eventually be blocked by closer objects. So you will end up rendering a lot of wasted triangles that will never show up in your image. So that is one of the inefficiency of this method. Yep.
Like, traditionally with the two bigger triangles and they're at the exact same depth. They're fine sort of handling that edge, or is that where it comes up to doing like the dead fighting?
Okay, right. Yep, that's a good point. So that's going to be a problem that we're going to talk about next. But any other questions before we move on to them? Okay, right. So this algorithm is very simple. We simply sort the triangles based on the distance to the camera. But it turns out this method doesn't work all the time. And in certain configuration of triangles, there may not exist a strict depth ordering for the triangles. So for example, triangles are not just discrete points in space. They have a certain area, which means that depending on how we configure the positions of the vertices of the triangle, we might get some pretty funky arrangements, like what we see on screen here, where the triangles might be overlapping in some places. One triangle might be in front of another triangle at some points, but it might be behind another triangle in different points. And in this kind of configuration, it's a little bit strange, but still a valid 3D configuration of triangles. But in these cases, there's no strict ordering of the triangles based on the distance to the camera. All of the triangles are sometimes closer to the camera than other triangles, but at other points, the triangles may in fact be further away from the camera than other triangles. So unfortunately, with this painter's algorithm, we can't correctly handle these more complex arrangements of triangles where there are overlaps between triangles, or where there are more complex overlaps between different triangles. Okay. So unfortunately, this painter's algorithm doesn't quite work with more complex scenes. And so this technique is generally not commonly used in rasterization pipelines. They do still have some useful cases, but a much more commonly used method for determining the order that we draw the triangles is by using a method called the Z-buffer algorithm. So the Z-buffer is also sometimes referred to as the depth buffer. And the idea with the Z-buffer algorithm is that we're going to try to directly store the depth of the closest triangle that we've drawn onto every single pixel. So given our image, So this is a frame buffer that stores the color values for all the pixels in our image. With the Z buffer algorithm, we are going to have an additional buffer called the Z buffer. And this is like an image. This is like a copy of our frame buffer. But instead of storing colors, the Z buffer is going to store the depth values at every single pixel. So similar to the frame buffer, every time we rasterize a triangle into the frame buffer, we store the color of the triangle that was drawn into each one of the pixels in the frame buffer. The Z buffer, on the other hand, instead of storing the colors of the triangles, the Z buffer is going to store the distance of the triangles to the camera that was drawn onto every single pixel. So every pixel in this frame buffer will tell us what is the closest triangle that was drawn onto this pixel and the distance that triangle was from the camera. Okay, so the way that this Z buffer algorithm is going to work is that at the very beginning, we have an empty frame buffer. We haven't drawn any triangles into the frame buffer yet. And so our Z buffer will be initialized to some very large value, like infinity, which is used to indicate that we haven't drawn any triangles onto any of the pixels in our image. Now, every time we draw a triangle onto the frame buffer, we are first going to perform a check between the depth of the triangle and the depth of the closest triangle that was drawn onto those particular pixels in our Z buffer. Right. So when we rasterize the triangle onto the image plane, we figure out which pixels are going to be covered by this triangle. Then for each one of those pixels, we check the depth value stored at each of those pixels. And then we compare that depth value with the depth value of the triangle that we're currently drawing. If the current triangle has a Z buffer, has a Z value that is all right. So if the current triangle that we're drawing has a Z value that is smaller than the depth value that's stored in the Z buffer, this tells us that our current triangle is closer than any other triangle that was drawn onto that particular pixel, which means that that triangle is not going to be blocked by any of the previous triangles, and we can color in that pixel accordingly. On the other hand, if we check the depth of our triangle against the Z values that store in the depth buffer, and we find that the depth of our current triangle is larger than the depth values in the Z buffer, then this tells us that there was a triangle that was drawn previously, which was closer to the camera than our current triangle. And so we'll not draw this triangle into that particular pixel because our current triangle is being blocked by some previous triangle that we drew. Okay, right. And this this Z buffer algorithm, by keeping track of the depth values at every single pixel in our image, they allow us to correctly order the triangles, to correctly render occlusion between different triangles for even some fairly complex configurations of triangles. So this Z buffer algorithm is probably the most commonly used method for handling occlusion in a rasterization pipeline, and is used in a lot of modern rendering systems as well. So this is a very simple method for figuring out which triangles are blocking other triangles. And for the most part, it's fairly efficient. It just comes at an extra cost of having to store the depth buffer. This just corresponds to storing an extra image in addition to the frame buffer that we use to keep track of the colors of the pixels. Any questions about this? Right. In this example, the triangles are not sorted. You can draw the triangles in any order you want. And the depth buffer will help to ensure that you correctly handle the occlusion between the triangles. So with this Z-buffer algorithm, you're going to get the same image regardless of the ordering that the triangles were rasterized in. Yep.
Would the Z-buffer algorithm perform the same as the Painter algorithm if you went in the order of the furthest away triangle to the front triangle?
Yep. Yeah. So performance-wise, if we always start from the furthest triangle, drawing triangles from the furthest triangle away and then moving towards the nearest triangles, then we're still going to more or less do the same amount of work as the Painter's algorithm. So we're going to end up rasterizing a bunch of triangles that might get blocked by other triangles. So in fact, the Z-buffer algorithm can be more efficient if you first render from the closest triangles and then moving towards the back, so that you can safely skip any triangles that are blocked by previously drawn triangles.
Does that make sense in terms of computing, to take the time and work to sort all those triangles before doing that? Does it actually save enough like work if we do sort the triangles first, then start?
Right, yeah, yeah, that's a good question. I'm not sure how much work you will actually save by pre-sorting the triangles, because sorting the triangles themselves can be kind of expensive, especially if you have a large scene. And also, depending on how complex the arrangement of triangles are, again, there might not be a strict ordering that you can sort the triangles. Right, yeah, so with this depth buffer algorithm, you can render things in more or less random order if you
Communication of the single moving objects and such. Would you need to recalculate the Z buffer for every frame?
Right. Yeah. So with the Z-buffer algorithm, you essentially you update the Z-buffer every time you draw a new frame. So every new frame, you clear the Z-buffer and then you redraw everything again. Okay. Okay, so this Z-buffer is a very simple algorithm. It works very well and is widely used in practice. But one of the key limitations of this Z-buffer algorithm is that it doesn't handle transparent surfaces correctly. So let's imagine if we have some triangles that are transparent, so we can see through some of the triangles in the scene. Now, let's say if we render the transparent triangles first. If we render the transparent triangles first, they're going to store the depth values of those transparent triangles into the Z-buffer. Now, if we try to draw triangles that are behind the transparent triangles, they're going to fail the depth buffer test, which means that they're not going to draw any triangles that lie behind the transparent triangles. And we'll end up not seeing any of the objects that are behind the transparent surface. So unfortunately, the standard implementation of this depth buffer algorithm won't actually work if there are transparent triangles in the scene. And handling transparent objects in a rasterization pipeline tends to be very tricky, and it requires a lot of additional tricks to try to render those transparent surfaces correctly. So for example, one trick that you might use for rasterizing transparent surfaces is that you might actually sort all the triangles first, and then draw triangles that are furthest away, and then moving towards triangles that are closer to the camera. And that will help you better represent transparent surfaces. But we won't go into the details of how you handle transparent surfaces, much more for rasterization pipelines. But we'll take a look at how you can better render transparent surfaces in the ray tracing lecture later. Okay, but if your scene only has opaque surfaces, then this Z-buffer algorithm generally works great. Okay. Right, so this is everything that I wanted to cover for rasterization. And at this point, you should have everything you need to complete assignment 3. So assignment 3, we will ask you to implement a simple rasterization system in WebGL. We've provided you with a lot of the scaffolding code, and you just have to implement some of the functions, like how to rasterize lines and triangles. So the assignment is going to be due 1 week from now, next Wednesday. So hopefully all of you have started taking a look at this already. For the most part, the amount of code that you need to write for this assignment is not very much, but there are some tricky bits that can take some time to get right. So for example, we're going to test your code on some edge cases, like the ones that we discussed in class. So you should test your code thoroughly to make sure that it's able to correctly handle all those edge cases. So make sure that there are no gaps between your triangles. Make sure that you get the same image regardless of the order that you draw those triangles. So even though the amount of coding is not a lot, it does take a little bit of time to get the details right. Any questions about assignment 3? Oh, right. So the edge case is what happens when a pixel lies exactly on the edge of a triangle. And to handle those correctly, we'll ask you to implement the top left rule. Yep. Yep, question.
Regarding the rasterization of transparent triangles.
Yep.
Would it be a sufficient technique to separate all the transparent triangles into a separate section and all the normal triangles in separate section? Rasterize all the normal triangles first, so that everything is connected, and then rasterize the transparent triangles, or with the assumption that the values that are there, I guess, doesn't get overlapped. Would we run into the same issue of Z is still it will still fail. It will still fail.
Yeah, so I think the method that you propose is reasonable, but it might not necessarily handle, unless you apply some additional tricks, it might not handle the case where you have multiple transparent triangles overlapping each other. So in that case, you still need to, you still might need to do some sort of depth ordering or something. Yeah, I'm sure trying to rasterize transparent triangles is a pain. But we will see later how ray tracing can provide us with a much more elegant way of handling transparent surfaces. Okay, any other questions for assignment 3? Okay, so please do get started on that soon. Okay, then we are going to move on to our next topic, which will be ray tracing. In this lecture, we're going to give a high-level overview of what the ray tracing algorithm is. And we're going to start with the basic raycasting algorithm, and then we'll take a look at how we can extend the basic raycasting algorithm to a full ray tracing system. And then after that, we'll take a look at some of the common computational challenges of ray tracing methods. And in the next class, we're going to go over some of the techniques that we can use to accelerate ray tracing. Well, at the start of the rendering lectures, we mentioned that there are two main families of rendering algorithms that are commonly used in computer graphics: rasterization, which we covered previously, and then the second class of algorithms, or ray tracing algorithms. So the main difference between these two classes of algorithms is how they determine visibility, how they determine which objects are visible at a particular pixel in our image. In the case of rasterization algorithms, we determine visibility by taking every triangle in the scene and projecting them onto the image plane. Once we have projected the triangles onto the image plane, we try to figure out which pixels are covered by the projections of the triangle. And the pixels that are covered by the triangle will be the pixels at which that triangle is going to be visible at in our image. So rasterization algorithms, they kind of take a shortcut by directly projecting triangles onto the image plane. Ray tracing algorithms, on the other hand, determine what is visible at a particular pixel by doing a more direct simulation of the behavior of light. In the case of ray tracing algorithms, for every pixel in the image, we are going to try to figure out which triangle in the scene is going to reflect light onto that particular pixel. So for example, if you have a simple scene like this, we are going to have a light source, could be the sun, which is going to cast light rays into the scene. To construct an image of the scene, we can try to simulate how light bounces around the scene, and then how much light is going to arrive at the camera to eventually form the image of the scene. So a straightforward way of doing this would be we simulate light rays being emitted from our light source. And these light rays are going to travel through the scene, and then some of those light rays are going to hit objects in the scene. When light hits the surface of an object, it's going to interact with that surface by either getting absorbed by the surface, or it might reflect off of that surface. And we can simulate lots and lots of light rays, and then as the light hits the surfaces in the scene, they're going to be reflected off in different directions. Some of this light is going to reflect in the direction of the camera, and the camera would then capture this light to form an image of that scene. Oh, push.
This sounds like, can this only be done efficiently with explicit like meshes where the outer edges of the model is defined, whereas
not necessarily. This ray tracing can be implemented using both explicit and implicit representations of shapes. And we're going to, in fact, the examples that we're going to discuss later in the class will be using implicit representations. But the caveat there is that we can really only use implicit representations that can be modeled by like a simple implicit function, where it's easy for us to determine the surface of that shape. For more complex shapes, it might not be as easy to find the surface. In that case, applying ray tracing to those more complex shapes can be more difficult. Okay, but for now, for some representation of the shapes in the scene, we can simulate how light is going to reflect off of the surfaces. Some of the light is going to reflect in the direction of the camera, but most of the light that bounces off of surfaces in the scene might be reflected in completely random directions that completely misses the camera. So one of the drawbacks with this naive direct simulation of light is that we can waste a lot of light rays that are never captured by the camera. So most of the light rays that we cast into the scene, most of the light rays that we simulate, they might just be reflected off in space, which means that they're never going to contribute to the image that the camera is going to produce at the end. And as a result, we'll end up wasting a bunch of compute simulating light rays that never interact with the camera, that never contributes to the final image. So the key idea behind ray tracing is that instead of directly simulating light rays, we are instead going to simulate reverse light rays. Instead of casting rays that start from the light source and emit out into the scene, we are instead going to cast reverse light rays that start from the camera and travel from the camera into the scene. And these reverse light rays, they more or less behave exactly like regular light rays. When they hit an object, these light rays will also reflect off in different directions. But the key difference between these reverse light rays and the light rays that we discussed previously is that every light ray that we emit from the camera into the scene is a light ray that will contribute to the final image because it is a light ray that's connected to the camera. So you can think of the light rays that emitted from the camera into the scene as potential paths along which light from the light source can travel through the scene to the camera. And this helps to make sure that every ray that we simulate will be a ray that contributes to the final image. Okay. So any questions about this? No?
Because if you take into account the texture of the object, of the light scattering.
Yep. Yeah, so a typical ray tracing system would take into account the different material properties of the surfaces in the scene. So it will kind of take into account the texture of the object, or like the different surface geometry of the object. Yep.
How do we pass the rate, the reverse light path direction back to the light source and have every single light beam go back to the light source? If when you're doing simulating light in reverse, you're shooting it everywhere, when they go everywhere, not just to the light source, and you're instead of the light source simulating it shooting everywhere, and some of it into the camera shooting everywhere, some of it's in the light source.
Right, yeah, that's right. Yeah, that's a great point. So when we're casting rays from the camera into the scene, those rays, when they hit an object, they might reflect off in random directions, which means that a lot of those rays might not actually hit the light source. And if a ray doesn't hit the light source, then there's no light that's going to travel along that path to the camera, which means that it also doesn't really contribute to the final image. But the trick in ray tracing is that we're going to trace a bunch of rays that bounces around, and we'll discuss this in more detail in a few slides, but we're going to trace rays that bounce off of different surfaces in the scene. And then at the very end, we're going to cast a special ray that's pointed directly at the light source. So you can think of this as we trace a complex light path that consists of lots of different segments. And then the very last segment, we're going to connect that back to the light source, so as to make sure that it forms a full path that connects the light source all the way back to the camera. Now, that being said, it might not always be possible to connect a point to the light source. Like there might be an object that blocks the point from reaching the light source. And we'll discuss how that should be handled. But yeah, so by always casting a ray at the very end towards the light source, this helps to make sure that we have a complete light path along which light from the light source can bounce around the scene and eventually reach the camera. Okay. So let's take a look at how we implement this ray tracing method. So the key operation in a ray tracing system is ray casting, where we cast a ray starting from some origin point into the scene. So every single ray that we cast into the scene is going to start at the origin of our camera. So this is the position that the camera is located in our scene. Starting at the origin of the camera, we're going to cast a ray, and each one of the rays is going to pass through a particular pixel in our image plane. So this ray is going to tell us how much light is going to travel from the scene and arrive at a particular pixel in our image. So we cast this ray that passes through a pixel in our image, and we then have to determine which objects intersect with this ray. Whichever object intersects with the ray will tell us the object that's going to be visible at that particular pixel. So if we cast a ray through a pixel and it doesn't hit any object, then this tells us that no object will be visible at a particular pixel. Whereas if the ray that passes through a pixel intersects with that object, this tells us that that particular object can be visible at a given pixel. So for example, for a particular pixel, let's say in the middle of this image, it might end up hitting the orange sphere. So this tells us that the orange sphere is visible at that particular pixel, and we might color in that pixel accordingly. So the key operation in a ray tracing system is to perform intersection tests between rays and objects in our scene. And this is a very simple pseudocode for how we can perform these ray object intersection tests. So first, we have a loop over all the pixels in our image. And then for every single pixel, we are going to construct a ray that starts at the origin of the camera and passes through that particular pixel in our image plane. Now, next, we're going to initialize a bunch of buffer variables to keep track of the closest object that intersects with our ray. So for a given ray that travels through the scene, there might be many objects that intersect with that ray. But the only object that's going to be visible, assuming all of them are opaque, will be the closest object. So when we are checking for intersections between a ray and objects in the scene, we want to find the closest intersection amongst all of the objects in the scene. And to do this, we keep track of a few buffer variables. Min_t, which corresponds to the distance, the depth of the closest intersection that we have found so far. And then we are also going to store an object pointer to the object that produced that closest intersection. Okay. Now, once we have constructed this ray, the next step is to loop over all of the objects in the scene. And for each one of those objects, we're going to perform a ray object intersection test to check for intersections between our ray and the objects in our scene. Now, for a lot of objects in the scene, there may not be any intersections with the ray, so we can just safely ignore those objects. But for the objects where we do find intersection, we have to do an additional check where we compare the distance of the intersection with this object with the distance of the closest intersection that we have found so far. If the intersection from the new object is closer than the closest intersection that we found so far, then we are going to update the intermediate variables to keep track of the distance of the closest object that we just found, as well as a pointer to that nearest object. And then we just repeat this process and go through all of the objects, and then we are going to return the closest intersection at the very end. And that then tells us which object is going to be visible at a particular pixel. Any questions about this? Okay. Oh, yeah.
How do you handle the data resolution for transparent object?
Right, yes. So this simple raycasting algorithm is not going to handle transparent, translucent objects yet, but we'll take a look at how we can extend this simple raycasting method to handle more complex lighting phenomena. So for now, we just assume all the objects are opaque, and the only object that we're going to see will be the object with the closest intersection. Any other questions? Okay. So with this raycasting method, we're going to loop over all of the pixels, and then we're going to cast rays for every pixel to find the closest intersection. So one of the most expensive parts of this raycasting algorithm is the for loop over objects in the scene. So if you have a complex scene, there might be many thousands of objects in the scene, and each object might be composed of hundreds of thousands of triangles, which means that there are lots and lots of ray triangle intersection tests that we are going to have to perform for every single pixel that we're trying to draw in our image. So the brute force implementation of this raycasting algorithm can quickly become extremely expensive and very slow. So in practice, we often have to rely on some optimization techniques, some acceleration data structures to make these raycasting intersection tests more efficient. We're not going to go into the details of how these acceleration techniques work in this lecture, but we'll take a look at some of the techniques that we can use in the following lecture. But just know that for now, this naive implementation of raycasting can be extremely expensive. Okay, but for this lecture, we are going to take a look into some of the details of how we actually implement this ray casting operation. So for every pixel in the scene, we have to cast a ray starting at the origin of the camera and that passes through that particular pixel. So to construct this ray, we're going to represent this ray using the parametric equation of a line. So RT here is a representation of our ray, where T specifies a distance along a distance from the origin. So given a particular distance T, RT is going to give us a point along the ray that is T units away from the origin. And this parametric equation of the ray can be constructed by using the origin of the ray, which can be the position of our camera O. And then it's going to add T multiplied by the direction vector of the ray D. So D is a unit vector that points along the direction that the ray is traveling in. So if we are going to travel T units along the ray, this corresponds to multiplying the direction by distance T, and then adding that to the origin of the ray. And that would then give you a point along the ray that is T units away from the origin. So to construct this parametric equation of the ray, we just need to determine the variables O and D. The origin is simple. That is just given by the position of the camera. But D is a little bit trickier to determine. So to determine D, we have to figure out a unit vector that points along the direction that the ray is traveling in. And to determine this direction vector, we are going to look at two different points: the origin of the camera and the position of the pixel P that the ray passes through. So the ray is a line that connects the origin and passes through the pixel P, which means that we can determine the direction of the ray by looking at the difference between the origin and the position of the pixel. So the direction vector of the ray can be determined by computing the difference between the position of the pixel P and the position of the camera, the origin O. And because the direction vector is a unit vector, we have to normalize the vector so that it has a length of 1. And so in the denominator, we are going to divide by the norm, the length of P minus O. So this is just taking the difference between the origin and the pixel position, computing the length of that, and then normalizing the vector to ensure that it has a unit length. And this then allows us to construct the parametric equation of a ray that represents all the points along the ray that's traveling in a certain direction. Okay. So for every pixel that we are going to draw, we are going to construct this parametric equation of the ray, and then we are going to use this parametric equation to test for intersections between the ray and objects in the scene. We probably don't have enough time to go through how the intersection tests are performed in this class, but any questions about how we construct this parametric equation of the ray? Oh, yeah. Yep, it's an O2 length. Yep. So that's just computing the length of the. So P minus O gives you a vector with some length, and we just calculate the length of that vector so that we can normalize it. Okay. Any other questions before we wrap up today? Okay, if nothing else, then we'll continue in Friday's section. There's a question. Oh, yeah. Yep.
For the top left,
Mhm.
criteria on the slides.
Mhm.
the coordinates that you use have 0 in the bottom left, right?
Right.
And then have the checks be based on that for the left side.
Right,
The,
yep.
the assignment has.
Yeah, the pixel coordinates are kind of flipped, so we'll just apply the rule according to like the pixel coordinates.
Okay.
Yeah.
Oh, yeah, so it would be visually technically on the right. But then that's.
Oh, sorry, visually should be top left.
Okay, so then. for
So
the
so in this case, like top like origin would actually.
Yeah. Okay, so then I think technically, because I was working on the assignments, I was doing this, the conditions are technically flipped then. Is that what the assignment's
Yes,
expecting?
yeah, it will be flipped.
Okay, cool.
Yeah, so the top left row should be applied like visually to the pixels on screen.
Okay, thank you so much.
I was just curious, like, any chance to know, I was taking a look at like the Wikipedia page on the OBJ file.
Mhm.
I was trying to implement something regarding it.
Uh-huh.
And I noticed there that it was listed as one of